reached over 70 people now, so I think we'll just get started. Can I please ask, if you're not speaking, to please use the mute button, just so that, awesome, thank you. Well, thank you all for coming. Just looking at who's here, I can see we have a good group of people today. So a good mix of distributors, retailers, Transpower, and both the public and private sector. So my name is Joey Au, and I'm the manager of retail and network markets at the Electricity Authority. Today's presentation is focused on Sapere's cost-benefit analysis of distributed energy resources in New Zealand, so by David, Toby, and Karina. Before I give some context for the work, can I please ask people to mute their microphones if you haven't already? And if possible, also turn off your videos. I know that some of us have very slow internet, or rather kids and partners also using the internet. And the last thing they want to do is just only hear every fifth word when I speak. As you are all aware, the authority recently published a discussion paper titled Updating Regulatory Settings for Distribution Networks. The discussion paper draws on a lot of great work done by the authority's Innovation and Participation Advisory Group, which is chaired by John Hancock. The discussion paper is currently up for consultation and seeks feedback on a range of potential issues and options on distribution networks. The authority's aim is to have the right regulatory settings in place to promote competition and access to the distribution network to better support the transition to a low emissions future at the pace required for the long-term benefit of consumers. Before I pass it over to the team at Sapere, just reminding everyone that this Zoom presentation is currently being recorded and will be published on the authority's website alongside Sapere's presentation slides. Sapere will present for 30 minutes, leaving 30 minutes for Q&A. If you have any questions, can you enter them into the chat function and possibly with the slide number, and the team will come back to them during the Q&A session. Without further ado, I'll pass it over to David, Karina, and Toby.
Well, thank you very much, Joey, and thank you everyone for attending. We've got a presentation here that we will now try and share. Does that come up all right? Looks like it has.
Yep.
Excellent. All right. Thank you. Well, Joey set the scene there, so I won't bother too much about the title. I'll just say that this is a pretty big presentation. We've actually done it to be a bit of a summary of the report, and it will be distributed later. But as a result, I'm actually going to rush through it and skip through quite a few slides and focus on the ones I think are most important. But any slide is available for us to go back and ask questions, as Joey said. So to go back over it, we were asked to do this cost-benefit analysis of distributed energy resources, which we delivered in July. I'd just like to point out that we actually have been thinking and working on this for quite some time. So the work that we've done in this most recent report is actually the consolidation of quite a lot of development work prior to that, right back to the Productivity Commission work we did, where distributed energy resources was a contributing factor. In terms of this report, the ones that come out most importantly is the demand response. I've actually got vehicle to grid in there, but that doesn't come out as being that significant. Demand response is very significant, and as well as all the potential smart home management and energy home management. I'd like to point out that does also include smart EV charging. That's a big component of it. And then we've got the rooftop solar, and we found that it's quite important in the future that these be paired with storage to be able to offer the most value to the grid. The question we were asked to develop a cost-benefit analysis of DER to realise it's unfair to potentially against a future where it doesn't, which is actually a little bit, that doesn't quite explain it. It's against a future where no further changes are made to encourage or to incorporate distributed energy resources, would be a better way of describing it. And most of us will be aware there are many problems in fully realising the value because it is quite a different technology and not one that the industry or the market or even the regulatory arrangements were really designed for. IPAG has identified a number of the issues that are potential problems for distributed energy resources. Won't go into those, happy to come back to that, but we'll take those as read for now. And in terms of this cost benefit analysis, it is the difference between a analysis that suggests what the economic benefits are of fully utilized distributed energy resources in the future, and a baseline. So it's not comparing a potential future against no distributed energy resources. It's comparing a future against a baseline that assumes nothing further beyond our current regulatory market settings, but there is still distributed energy resource take up. So that's the key difference between our assessed what we call factual and the baseline. And we still have DER in the baseline, and that DER take up is based on the Climate Change Commission headwind scenario. We'd like to stress that both scenarios are trying to meet significant demand growth through electrification for New Zealand's decarbonisation efforts. So they both have significant demand potential to meet in the future. In terms of our approach, we were looking to apply a traditional supply and demand concept, which economics uses a lot. So if you have a demand curve and a supply curve, you get an intersecting point, which is a market equilibrium, and that sets the benefits in terms of what people get out of the service, less the costs. And that difference that you can see in there constitutes the economic benefits under a supply and demand analysis. Again, stress that this is the difference between two supply and demand intersections, not just a single one. So it's our assessed future less a baseline is how we calculated it. That's an idealized supply demand curve on the left. Just stress that as with most industries, real supply demand curves don't tend to be smooth. And we had a significant issue in comparing capacity services and energy services on the same curves. And therefore we needed to come up with a slightly strange unit that incorporated predominantly capacity, but had a time dimension so that energy products were considered. And that unit is the dollars per kilowatt per annum. And the other quite strange thing about, or not strange, unique thing about this analysis is that not all DER can provide all grid services, and therefore we've used what we call a conditional supply curve to do the analysis, and I'll come back to that more later. In terms of understanding the potential value, we actually started with the international work and the traditional value stacks that they were using. We did find that we needed to modify those a bit and put them in the context of a New Zealand demand stack. So rather than dwell on those international value stacks, we'll move on to what we did. So a demand curve sorts the value streams in descending order. It comes under the principle that you apply resources to the highest value first, and then you go down the demand curve until you reach the point where it's not worth supplying that extra demand because it costs too much. We haven't done unfettered supply. So the demand curve, we'll come back to the demand curve, but we haven't done an unfettered supply. We've tried to do a credible assessment of the potential contribution of distributed energy resources rather than necessarily looking at all the service that could be offset. It's a particularly difficult exercise because we found that not all value streams are additive. So when we moved to different parts of the curve, it wasn't a case of saying, well, those costs are reduced, so you move down the curve. There are some value streams that actually replace rather than subtract from value. So for example, if the requirement to offset new lines and generation is met, we don't then assume that you still need to offset voltage regulating equipment. We've anchored our zero axis at 30 cents a kilowatt hour. We did suggest that with the peak demand growth that you might have in a future where DER isn't coordinated, that the prices could go higher than that. We just decided to be conservative and anchor that to 30 cents a kilowatt hour. We didn't try to do any analysis of what that future price may be. And we limit price reductions in the demand curve so that at no point the price that we can come up with can be less than the value of the residual grid services. Now I've got a few slides that says how we came up with those value bands. I'm going to skip over the ones, frequency keeping instantaneous reserve. The assumptions are there. We're happy to answer questions later, but it's really not material. Resource adequacy, remove existing thermal peaking, was significant in 2021, but doesn't offset the key value drivers once you get out into the future. We tried to be reasonably conservative, so we've only assessed that about half of the current thermal peaking could be offset, and we've used the variable cost of peak generation. We haven't assumed that you would recover any sunk or stranded costs. Resource adequacy, offset new lines in generation. This is the most significant value band in the analysis, and distributing the new resources could help reduce peak demand. A significant amount of this new peak demand is actually EV charging, which could potentially be very significant. And we'd like to stress that in terms of offsetting this peak demand, we are only looking to offset new peak demand. We have not assumed that there would be a reduction in existing capacity. Potentially DR might offset some existing capacity, but we've assumed that we're only offsetting stuff that would be avoided in the future. In terms of the 2021 volume, to be honest, it's a relatively rough guess, but it's a small number, potentially 100 megawatts that could be offset through the use predominantly of demand response. But in 2035 and 2050, we've got volumes assessed on the basis of the peak demand analysis from Whakamana i Te Māori Hiko. A huge amount of that was electric vehicles if they're not coordinated. So you can see there the bulk of the 1900 megawatts in 2035 and 2900 megawatts in 2050 is uncoordinated EVs. And then residual peak demand that could potentially also be offset if there was no further thermal, and maybe some retrenchment of some other capacity, which we've just used former auto units as a proxy for. It gives you 2,400 megawatts of demand avoidance potential in 2035, and 3,300 in 2050. In terms of that cost breakdown for the $237 a kilowatt per annum, that breaks down to $73 a kilowatt per annum for generation, $68 for transmission, and $96 for distribution. The generation costs are based on partially loaded geothermal, so we have assumed government policy of 100% renewable by 2030. So we've looked to a renewable substitute for peak generation. It offsets transmission costs based on Transpower's assessment in Whakamana i Te Māori Hiko. And the distribution cost is also from Whakamana i Te Māori Hiko. But we did talk to Transpower about the methodology that they used in that, and satisfied ourselves that it was a reasonable approach. Our understanding of that approach is it was based on some analysis done by them by Stakeholder Strategies, where we understood it prorated Transpower's capital costs with distribution capital costs in proportion to the growth projects in Transpower. Noted that seems to be a little bit of a controversial number, so very quickly have done some order of magnitude assessments based on Commerce Commission disclosures. And you can see there from 2013 to 19, the increase in transformer capacity in the Commerce Commission disclosures. That's not a perfect proxy for megawatts, but in a relative sense, there was growth of 2,340 MVAs. and system growth costs were almost $1 billion. We ignored the 2020 numbers because there was just a huge capex, huge system growth capital spend in that year and a very small increase in capacity for some reason. So ignoring 2020, it implies $420 to $426 per kVA per annum. And I'll stress these numbers are really just indicators. Those numbers include new lines and new connections. So for context, from 2013, customer numbers and line length increased to about 4 or 5%, where transformer capacity increased by around 12%. So that suggests that maybe in the order of half of transformer capacity was increased due to increased peaking rather than new customers and new lines. Very rough analysis, but it just gives me a bit more confidence that the order of magnitude of around $100 per kilowatt is credible. Offset voltage management assets. I don't want to spend too much time on this one because it actually doesn't affect the valuation. It's completely offset by resource adequacy, offset new lines of generation in 2035 and 2050. And in 2021, the clearing point doesn't actually reach it, but we did actually find there were a few errors in the assessment of the voltage management assets. We reported a couple of numbers wrong in the report. And we were actually more conservative than we said. And in fact, we only ended up putting in the MVAR number instead of the megawatt number, which should have been higher. Don't want to dwell on that because, as I said, it didn't actually affect the outcome. Harmonic filtering, the assumptions are there, but it's a negligible effect. And hydrotherming is the other very significant one. And that's simply based on analysis from NIWA's climate information that 5,000 megawatts of solar PV, which you would have to have batteries and demand response with to manage short-term consumption profiles, but that theoretically could provide 3.1 terawatt hours of winter energy, which would meet the winter energy margin for hydrotherming. Costs are based on offsetting thermal generation, again, variable costs only, at a dry year average of 1 in 4.5 years, which is using a recent averaging on dry years. Duplicated a bit on the demand curve, but all I will add here is just to reinforce that it is a complex demand curve. Have had to use judgment to shape that curve. It often isn't as simple as implied, and we didn't want to add any extra complexity to the demand curve, so that conditionality we talked about for distributed energy resources not being able to supply that demand curve, all types being able to supply all parts, and we've built that conditionality into the supply curve. So we order those volumes and values in decreasing order as discussed, using judgment about when it's offset, when it's added, or when it's simply replacing, and by stacking them along the volume path and with decreasing price, we create that demand curve for 2021. The 2035 demand curve is significantly different because there's much more potential to offset new lines of generation with those significant growth in peak demand. And then 2050 is very similar shape, but with bigger numbers. The supply curve, that builds up potential supply in ascending order of costs. So you use cheapest production first, but we also have to meet this requirement that the DER that's used to meet that section of the demand curve must be capable of providing that service. That conditionality is taken from this following capability map. So those brown squares indicate where we have assessed that that type of DER is capable of providing that service if it's coordinated. And the big difference between our full DER potential assessment of value and the baseline is that they've got it's a different capability map for the baseline. So in the baseline, much less of the services can be provided, and really the only one that most of the DER can access is the potential to offset thermal peaking through market prices. In terms of supply costs, I don't want to delve into too much detail here, although we're happy to come back for questions. We just want to point out that we've used international research on future of costs. We've definitely tried to put that in the New Zealand context, so we've been mindful of costs in New Zealand. And the supply that forms the key parts of our supply curve we've just highlighted there. Happy to come back and talk about that further in questions, but we've got the details on how we came about that. In terms of the demand response, we're very much looking at incremental demand response, so that's why we haven't included water heating. Water heating is already controlled, so we haven't got that on an incremental basis. And just re-stress again that a significant part of the volume that's capable of being responded to comes about because of electric vehicles. Solar PV and storage, again, our assumptions are there. Happy to come back to them on questions. The only thing we'll point out is that we don't actually have energy service on our demand curve. So the cost of solar and PV is actually their cost net of energy supply. So it's the residual cost that's available for other services that we've put into the supply curve, which is the same for commercial as well. Just a note on the commercial, we did have the numbers in the report are slightly wrong. We didn't pick up a discount range change. The numbers in the model using the 6% discount rate, but the numbers we have in the report need to be adjusted. So we get the supply and demand curve interactions, and in 2021, with a limited supply, we found that the potential is there to offset our very rough assessment of new lines of generation with demand response, and that creates a value on the front end. That is a relatively small component of the total value, which we'll come back to later. In 2035, that's when there's a significant increase in the potential value, the value being the difference.
Just do the copy in sort of thing after you have a talk with them. Just tell us where you got to, and then we'll follow up for you. All right.
Whoop.
Awesome.
Okay.
Have a good day. Bye-bye.
The value of the supply and demand for each scenario is given by the difference between the demand curve you can see there and the red supply curve. So you can see in this case, we're making substantial use of demand response and then starting to use photovoltaics with batteries to help get to the point where you're offsetting peaking and potentially even maybe offsetting some hydrotherming. And then in 2050, there's even more demand response and photovoltaics available. Again, a lot of that demand response is coming through electric vehicles. So that comes down to, if we have a look at the cash flow over those periods, you can see that a huge amount of the net economic surpluses, so this is the difference between our future and our baseline, is occurring in the future. In terms of absolute value, we get to 2050 and those values are very large, but on a discounted basis, they actually peak in 2035. So that simply means that while they're still growing very strongly, the growth in value post 2035 is less than the 6% discount rate. And you can see that the values actually start quite low and grow strongly to 2035. Okay, sorry, I'll just work out how to change my screen around a bit so I can see any questions. Do we have any questions? Or am I just simply not? Oh yeah, here we go, sorry. You mentioned DR capacity limits, assuming slide 6, what assumptions be made regarding network investment levels and extent to which distributors should be providing unconstrained networks. The investment, so we've made the assumption that in the absence, so the two assumptions are in the absence of coordination, that generation, transmission and distribution capacity would need to be built to meet the resulting peak, and we've made the other assumption in the factual that DER is well within the some of the conservative assumptions we've made, that DER is deployed perfectly to avoid network investment where it can. But we have tried to be a little bit conservative in our numbers. Oh, sorry, just trying to scroll down. Oh, gosh. Oh, sorry, operator error. I can't make that move. Oh. I've gone one extreme to the other. My apologies. I'm having trouble getting my slide 11 and others. How sensitive is analysis to the $90 megawatt hour for thermal peaking? It's actually not very sensitive to the thermal peaking number at all. It really only has a significant impact in 2021, where you can see from the cash flows that it's quite low. Sorry, the net benefits are quite low. And then by the time you get out to 2035, the residual grid values of hydrofirming and offsetting lines means that the thermal peaking offset doesn't make much difference. So that doesn't make much difference to the result. Is the net economic surplus in 2050 accumulated?
No, that's per annum, David. Yeah, so that's cash flows per annum. Yep.
Yeah. So so it's accumulated in the NPV, but those cash flows, probably not strictly cash flows, they're value streams, but they're not accumulated as per annum. I apologize if I miss a question, but my computer's responding slowly. On slide 28 and 29, question regarding the timing and quantity of DR from smart home DR, rolling out retrofit DR, retrofit to existing appliances via smart home thermostats. I was wondering if you have the same potential in New Zealand. Your numbers between 2021 and 2035 may be somewhat conservative. We have tried to be conservative, so it wouldn't surprise me, although I dare say that that different people will come up with a range of different forecasts for that. But we do think the numbers we've come up with are credible, and we have not tried to be over-optimistic. How have you treated distributed generation, which can provide, oh gosh, sorry, I really am struggling with this. How have you treated existing distributed generation, which can provide many of the identified services? We have identified, you see in 2021, that demand response could make a contribution now. In terms of many of the other distributed energy resource services, well, there's actually not that much benefit beyond demand response that can be provided, but in terms of particularly PV and batteries, we haven't assumed necessarily that they've got the type of connection that could be coordinated. That's not universally true. We're aware of some that probably can, but there's probably also a lot that can't. David, the avoided dollar kilowatt figures look to be important for part of the value stream. What do these translate to in reality for Transpower and EDBs? Slightly unsure of the question. I'll try and answer that question if I've interpreted it correctly, but what we're saying there is that if you had the coordinated scenario instead of the baseline, that you would avoid sufficient peak capacity to be able to save the volume of capacity times that dollar figure in annual terms, in terms of distribution lines or equipment that don't need to be built, transmission lines and equipment that doesn't need to be built, and peak generation capacity that doesn't need to be built. I'm not sure if that answers your question, sorry. Is the assumption made that DR is always able to deliver a service if it's capable, or is there a performance factor applied to the devices? We didn't actually apply a performance factor to the devices, but we tried to be conservative. For example, only assuming that it could offset half of the thermal peaking. We're probably a little bit more bullish on the avoiding peak capacity, but that's again not offsetting existing. In terms of, well, that's not a good example because it didn't make much effect, but we were quite conservative of what it might be able to do for voltage management. So no, we haven't applied a performance factor, but we have tried to be conservative in benefits. Oh, okay. Now I'm a bit worried that I've got operator error. I'm not showing any more questions.
Hi, David. I think you've missed one a little bit further up from Nathan that says, what do you assume in EV charging behaviors between the baseline and optimal use?
So the difference in EV behavior between well, effectively it's that the coordination of EV charging is done in the ideal scenario so that it does not contribute to new peaks. That it is, well, doesn't contribute to new peaks in excess of a base load capacity in aggregate. Hopefully that answers the question.
And David, can you see Matt Smith's question? I'll read it out. Is the assumption made that DERs, you got it?
Yes, no, I thought I'd answered that one. That's the one about the performance factor, which we haven't applied, but we have tried to be conservative about contribution in places.
So David, just rather than type a question, and to elaborate on my question about EV charging behaviours. So was your answer that in the baseline you've got sort of essentially uncontrolled EV charging, that there's no attempt at sort of managing people coming home from work and charging their vehicles, whereas in the optimum or ideal scenario, all of that there's effectively no contribution from EVs at peak. Is that what you're saying?
I'm saying, yeah, under the baseline, that under the current regulatory settings, there's no mechanism by which they would be coordinated, and therefore the only limit on peaking would be diversity. And under the ideal situation, they are managed in such a way that they don't contribute to peak in excess of a base load equivalent, if that makes sense. Sorry, just
Hey, David, I think we have a related question on the chat.
Yep.
So related to the previous question, does the analysis assume AS/NZS 4777.2, simplistically capacity for centralized control of DIR inverters by DSO/TSO has been mandated in New Zealand? Question.
It implicitly does. I would just say that the capability of the inverter is one half of the coordination question. You also need the coordinating system, and you need the right incentives for coordination, and you potentially need the right incentives for the sizing of the installations. So we haven't, that assumption hasn't changed anything in our analysis. We've assumed that by itself doesn't lead to a different outcome. It's difficult to, yeah, I don't think it's very sensitive to those Part 4 incentives. We have assumed, which I think is a reasonable assumption, that if the way I've looked at it is that so this is the chicken and egg thing that we've talked about quite a lot in IPAG forums, but in the absence of certainty of both large numbers of DER, so you can rely on statistical compliance, and on the reliability of the systems that coordinate, it's described, I think, it says have incentives to refer their own investments. I don't think those incentives are entirely economic. I think that from a security supply point of view, where it's quite critical to ensure security supply, that any uncertainty will potentially lead to those preference for investment. So I do think there is a very difficult transition to move from our baseline to an ideal future. We've done the valuation on the basis that you can achieve that. I would like to stress that my personal view is that that is not easy, and it is a challenge for the industry. Where does the impact of real-time pricing sit in the scenarios? Real-time pricing will sit in the, real-time pricing would have an impact at the wholesale level. So we have assessed that would not wouldn't necessarily under current market and regulatory settings mean that you had that incentive at the retail level. So that hopefully answers that question. One aim of the authority's ongoing distribution pricing work program is more efficient investment in the operation of DER. Is that an EDB price reform roadmap's factored into the baseline scenario? It isn't really, is the easy answer to that. And this is one of the difficulties that we had, is assessing what it means by current regulatory settings. So on the basis that there is still some work to do in that work program, we haven't assumed that it makes a difference right now. It could be argued that maybe that's a certain piece of work that would deliver benefits, which if we use that to change our baseline, it might make some difference. All right, so I'll just get back up to you. Following on from RTP, is it assumed in the baseline that DER doesn't respond to real-time wholesale prices either individually via retail market or aggregated? We assessed what would be confident So my answer to that would be on current market settings, you wouldn't be confident necessarily that all retail DER would respond to real-time wholesale prices, because the truth is most of it doesn't really have those signals at the moment. There's a judgment in that, because there certainly are parties that are doing that now. So that could be an area we should take a better look at. It does require a higher investment in the actual equipment though. So I think our analysis suggested that at this point in time, you wouldn't necessarily invest in that unless you had a very specific business plan in mind, and faith in the future, I guess I would say. Part of any benefit of DER can be achieved by simple, or rather traditional distribution transmission pricing, e.g. time of use can only be part of overnight encourage batteries V2G, and any part of any benefit of DER can only be captured in binary real or real-time pricing. Any thoughts on what contribution each makes? We found perhaps less by the end of the period because the costs of DER fell so much, but at the start of the period, unless distributed energy resources were able to get all value streams that they might usefully be able to contribute to, you probably get delayed take up. And I think the concern is that you have distributed energy resource growth without an investment signal early enough, then you have a lot of technology put in place that actually doesn't have the capability to do these things later. So my rather abstract answer to that is I think they're both equally important. Does your analysis provide any insight as to where the industry put its focus first in ensuring we have capability to use DER optimality? The authority is seeking feedback on its priorities. So does your analysis shed any light on where it should put near-term efforts or the technologies it should focus on? In terms of the near-term efforts, our analysis probably didn't break that down well enough to come to a conclusion. In terms of the technologies, demand response did seem to be a very important and cheap and effective technology in our analysis. Some of that needs to be better enabled through technology, but that does look like one with the front end, where the front end benefits occur. So that might imply focusing on price and incentives, but again, I would stress that you probably do need to be holistic in the approach. Does the analysis, how close can regulation reasonably get to the forecast ideal world? Oh, that's a good point. Obviously, regulation is only one part of this. I guess I should say that our cost benefit analysis wasn't to try and assess the benefit of regulation. It was to try and assess the benefit of getting to the ideal future. Regulation is part of that. There are lots of other parts of that. And again, I think it's a difficult transition that anyone needs to play a role in to get there, would be my view. Does the analysis break down the benefit sources by time and source for the scenarios? The benefit sources by time and source for the scenarios. It probably does, doesn't it, Karina? I'll better let you answer that one.
The report provides a breakdown by the value streams. So if that is included as aggregate, but I guess we could do a time series as well if needed.
Yeah, so we probably have breakdowns more than we've reported on potentially. So if that breakdown by value stream isn't adequate, we probably would be able to derive it. Is that, have I missed any questions? Oh, what's the percentage? Oh, hang on, David, I'm missing a question here. You mentioned the baseline includes an assessment of the diversified EV charging load over what level diversified load you assumed per household or per vehicle. It would be the same assumptions that were used in Whakamana i Te Māori Hiko. I actually couldn't answer that off the top of my head. I don't know if you could, Karina, but we could come back with that.
No, I don't have the numbers by household or by vehicle, but I know we used the 30% diversification factor. Yeah, based on the Whakamana i Te Māori Hiko and assumptions on transformer capacity per house.
What is the percentage difference in DER and baseline and counterfactual? Gosh, I'm not sure off the top of my head, Karina.
No, sorry, Rob, I don't have that either. If you don't mind sending an email, and I'll reply.
It's going to be pretty big.
Yeah, definitely.
I don't see any more questions here at the moment, but I think oh no, here we go. Sorry, I think there's a bit of a delay in me seeing what's coming up. Okay, oh, good work, David. I think you have credibly, if somewhat conservatively, shown the value of this work stream, but agreed that work stream faces challenges. Oh, thank you very much. I accept that not everyone may feel the same way. What is the non-baseline scenario most sensitive to in terms of assumptions? It would be the capability, that capability map, particularly in contribution to avoided new avoided lines in generation and new generation and lines. So any change in assumptions about the contribution to those bigger value streams in that capability map on the baseline, that's what would be most sensitive to. That would be right. You'd agree with that, would you, Karina?
Yes.
Is the non-baseline scenario sensitive to uptake rates of DER and social costs and technology? I think the answer to that is yes. It would be sensitive to it. You'd have to have quite a big change in the, yeah, I mean, it would need quite a big change in the uptake rates to make a big, well, it would make a significant difference, but it would take quite a lot to make a very, very large difference. It would be far more sensitive to a conclusion that the DER couldn't actually provide those services. Could you interpolate the avoided investment in distribution, transmission, etc., from your analysis? I think the answer to that is probably yes. Yeah, we should be able to. We've got price and volumes, or cost and volumes. Okay, I'm not seeing Any more questions? Although I'm not entirely confident I've seen them all, or that I'm updating fast enough. We might be in a place, Joey, where we go back to you. I guess we should say that, as you said, we have found some what seem to be minor errors, which we will correct. This presentation will be made available, and if people do have further questions, then we'd be happy to answer.
We could also ask Joey, where do you go given this work? What's next?
Yep, just give it a while people are thinking of questions. Otherwise, yep. So basically, the where to from here is essentially this is very much the start of the process, because this was a piece of work that the authority wanted to have done just to give ourselves a better sense of what the size of the prize were in terms of the DER space, and the progression of this work in parts is about the sort of submissions process that we will receive as part of our consultation paper. So that's really the vehicle and the channels to digging further in terms of the issues and the options, and also further analysis around CBAs of other options, etc. Okay, if we don't have any more questions, I think we might just leave it there. I just want to thank David, Karina, and Toby and the wider team at Sapere, just for the presentation, because I know it was quite hard to say stuff and not being able to see anyone to give you a reaction of whether they're nodding or shaking their heads or whatever. So, and also conscious of the IT issues as well. So thanks, David and team.
It's a brave new world we all have to get used to, isn't it?
Yep. So we just got 2 more questions, which I'm happy to try and quickly cover. So one is about the timeline for the next steps. So basically, the authority's discussion paper is currently up for consultation, and that's current submissions close on the 14th of September. But having said that, we have received a couple of comments from stakeholders about wanting a bit more time. So we're currently just considering that at the moment. And so given the current focus on the battery project in H2, is there scope for this work to be given more attention by the Minister? I think it's fair to say a lot of the authority's work in this space is actually shared with other government departments, etc. And also it's aligned with the government's wider goals around the low emissions future. David, I think there's a question there for you, if you can see it.
Yes. So in terms of have we factored the incremental cost only of additional capacity rather than the total cost of new, that is what we have assessed. So remember, it's assessed against a baseline, and the assumptions in the under the ideal and the baseline have the same growth in total energy consumption and therefore new connections and new lines and transformers. So the difference between the two is the incremental.
And just to answer the clarifying points around after the consultation. So basically after the consultation, the team at the authority would be summarising all the submissions, and also I hope to reach out back to retailers, distributors, and other sort of stakeholders, just to ask some more questions or having a bit of a discussion about what we're starting to think about in terms of their submission. And then I think it'll be a case of what we find, I guess, in terms of the evidence through that process around the issues and options, etc., before we do more analysis into them. Okay, I think I'll leave it there rather than just stare at a lot of names and not seeing a reaction. So again, thanks to Sapere for their presentation. And also just thank you everyone for taking the time out to hear about this work and ask questions. Okay, see everyone.